said in the case of AdaBoost, we can have any weak learner, right? And the idea could be why, normally, as we said before, that in literature, most of the time, the weak learner, the example is given is a decision stump. Or it could be generally, practically speaking, it could be other linear classifiers like logistic regression and other stuff, right? Of course, practically speaking, SVM is not used because single SVM training itself is quite consuming. And one of the issue with AdaBoost, anyone who remembers what we discussed, one of the issue with AdaBoost ensemble learning is?
Too much time and training?
Yeah, training time is sequential. It takes a lot of time, right? So then the idea here was, what's the good point of a decision tree? So if you're speaking about a single decision tree, I'm sorry, if you're speaking about a decision tree, what's the good point of decision tree? It's
the training time is logarithmic.
Yeah, simple and intuitive, right?
Yes.
And it has low bias but high variance, right? Decision trees can overfit. That's one problem with decision tree. One of the thing is it can overfit very easily. Right? This is the major problem. So the good thing is it's simple and intuitive, easy training, and it has low bias, but it has high variance. So this is actually not, it's actually, I'm sorry, it's a downside, okay, of decision tree. So the question is, why not have an ensemble of decision tree, individual weak classifiers? Let's assume that the whole decision tree is as an element of ensemble learning. But one possibility is to use decision trees with AdaBoost, right? So you use AdaBoost, and in AdaBoost, individual classifier is a decision tree. So each weak learner is the decision tree itself. This is good, but the problem again is that AdaBoost, the training is sequential. It takes a lot of time, right? So there is another improvement, which is by the name of random forest, the idea of ensemble learning with decision trees. So the idea here is to create a forest of decision trees. So you have a number of decision trees. I don't know how to make it, assuming this is some sort of decision tree. So now you have a forest of trees. So you have a collection of decision trees. Okay. And what you do is these collection of decision trees are treated as ensemble. So you do some sort of voting over it. So this is the idea of a random forest, right? So let's go to the technique, the random forest technique. What does it say? So it says given a data set S of n label points, right? You decide how many in your random forest technique, how many individual trees you're going to build up in the ensemble, how many trees you want. So let's assume it's capital T, right? So this capital T is going to tell you the number of individual trees you have. Okay. Now, what do you do? How do you train these individual trees? There are two major points in random forest. One of the thing is that for each tree, you train using the concept similar to the bagging up, the idea of bagging. So you do what? You choose n prime random samples from the training with replacement from the original training set. And normally n prime is same as n. So basically it's the same idea of bagging. So you if you have three decision trees to train, you're going to create t batches of training set. T batches of training set. Of course, each of these P batches is how you generate them is the same idea of bagging. Okay, but then what do you do? How do you learn? Now the another aspect of the decision tree is this, that fit a decision tree H3 to these points at each node. What you do is you don't use all the features you have. You only restrict to K features from all the features. And these K features you select at random. And normally it says that K should be square root of D. So assuming that you have 100 features at any node, once you're doing the splitting, you're not considering all those 100 features. You're only using, for example, square root of 100, which is approximately 10. If you have 1000 features, you're going to use square root of 10, which is something close to 30 something, right? 33 or something, 33 features. So there are two places where you have randomness. You have one is the aspect of randomness because each tree is built on a slightly different training set. It's not exactly the same training sets, right? The other thing is that the tree is built based on only a subset of randomly selected training samples. Is this idea getting clear? Do you get these two major ideas of the random forest? So first you decide how many trees you want, individual trees in your random forest. Then you do some sort of bagging to create these batches of training set with replacement. And then for each decision tree, you're going to train on one batch of training sample. You select only a subset of features randomly selected. Randomly you select them. And you split the node of that tree based on only those subset of features, not all the features. So in a sense, each tree is not exactly same in behavior to the other tree. So you basically end up with T trees, and how you do the final classification. The result of each model is combined by averaging the output. If you're doing the regression, the output of each tree, you just do the mean. And in case of classification, you do a majority voting. So the same idea, how you do the combination of the ensemble. So you just do a majority voting of from among the T trees. And this is how you do the final classification. Is this idea clear of the random forest? It's basically knowing other ensembles so far, the ADA boost and bagging, it's very straightforward to understand, I believe, the random forest. But again, it's very powerful. And again, it has all those good qualities of ensemble learning. So it's very robust to overfitting. And it's one of the most powerful classifier from if you see just off-the-shelf classifiers. So if you want to do any classification problem or for that sense, even regression, and you want something very quick, this is one good classifier to try, random forest. So good. So one thing, so what do you think about the hyperparameters? What are the hyperparameters you have in the random forest? What do you think?
Number of trees.
Of course, one of the most important thing would be the number of trees you have. Okay, but then there can be other fine tuning you can do. The default is that you have square root of b as the subset of features you decided based on which you're going to split. Okay, so this can be changed. This is another thing. And the third thing is also that each decision tree, the parameters of the decision tree, how deep you want to go, the depth of the tree, for example, you can even decide that. And it has been found empirically, very interesting findings that if you have a very noisy training set, okay, having building a random forest with very shallow decision trees actually does very good. So this is one insight into this. But of course, the most important thing is the T, the capital T. How many individual decision trees you want to have in your random forest. This will be the first most important hyperparameter. Once it comes to libraries, again, in Python, for example, you can have in scikit-learn, you have this classifier called random forest classifier. You can create an instance of it. Then you can say fit. And finally, you can do a scoring or a prediction. So there's fit method is there, score is there, predict is there. And then you can see in the random forest, once you create, by default, there are some parameters set and you can modify those, right? So it's good to also get familiar to it. We'll have an assignment where we are going to use ADA boost, bagging, and random forest for classification. So that will be also a nice place where you can try different parameters and try changing some of the parameters and see how it affects your problem, your classification results. Good.
Sorry.
Yeah.
You said that random forest also perform reasonably well in shallow features. So that is
no, what I said is this, that one of the thing we said is the most important hyperparameter. hyper parameter for random forest, the most important is the number of trees, right? Which was shown as capital T in the previous slide. This is the most important one. I said there are other parameters also. One of them is we said that we randomly select among k features from n total features, right? Now this k is normally set to square root of n. Now you can also set that. You can say, okay, this may not be square root of n. This could be square root of 2n or square root of other value, right? Or you can fix it to be in a given problem. For example, you have 30 features. You say, okay, k for me is 10. You can set these values. This is one of the hyperparameter again, right? Normally speaking, for classification, square root of n is used by default. And the third thing I said is once we are deciding the random forest, we know that individual classifier is a tree. So one of the important thing is also what is the maximum depth of the tree? Depth of the tree. And what I said, yes, please. Yes.
Regarding K here, when you said 10, you mean each decision tree will take 10 feature from out of 30?
Yeah, so you're saying instead of using square root of 30, which is like close to, let's say 6 or even between 5, like actually it's the floor of square root of 10. So it's 5, right? So instead of using 5, you think, okay, maybe in this problem, that's not a good idea. Let me set it to 10 features instead of 5. So 10,
yeah, but you mean that
10 random features you select from among the 30 to make a split of a node. So you're only selecting 10 out of 30.
Each split will go.
So each split will only use by default. If let's assume you have total features of 30, and you by default it will use only 5 of from among the 5 square root of 30. So it says a floor of square root of 30. So which is equal to 5, right? So it's going to use only 5 of the features selected randomly from among 30. So you can say, no, in this problem, let's not use 5, but use 10, for example. So this could be a hyperparameter to try out. Another hyperparameter I'm saying is to set that once you're creating these individual trees in your random forest, what should be the maximum depth of tree? How deep each individual tree should go. And here I said that one of the interesting findings was there that if you have a very noisy training data, your training data is very noisy, okay, then having shallow trees, for example, trees with, again, depends on problem, but assuming instead by, let's say in a common problem you had 100, the maximum depth of the tree, if you use, for example, shallow trees of depth 10 to 15, it works quite robustly, even though you have a very noisy training sample. What do I mean by noisy training sample is that the labels, your class labels on the training samples are wrong. Many of them are wrong because of human error, because of labeling, manual labeling mistakes, or some other reasons, or data corruption. If you have highly noisy training samples, I mean highly noisy training samples means the class labels of the training data are, many of them are wrong for some reasons. So if you use a very shallow decision trees in a random forest setup, it performs quite robustly in those scenarios. This is just one finding, recent finding, which I thought is good to share. But again, going back, the most important hyperparameter is the number of trees you have in the random forest. I hope this is clear now.
Yes.
Any other question before we move to a new topic?
Doctor, I have a question.
Yes, please.
Yes, one question.
Yes, please.
Is there any chance there's going to be overlap between features between the trees in the random forest?
Of course, there will be, right? You're saying you're going to select at every split node, you're going to select a k out of n features randomly. So of course, there will be trees where there will be the splits will have some common overlap, but not as a whole tree. So the idea here is you will have less correlation between the trees. Because again, there are two places of randomness here. One of the randomness is the training sample itself. We said that the idea is coming from the bagging idea, right? You create different batches of training for each tree, where you, for every batch, you draw from the original M samples with replacement. the same idea of bagging. But not only that, you want to uncorrelate the trees you get as a result. So you're saying, okay, don't let every tree decide from all the features at every split. You only select randomly k of the n features to decide on. So this helps also to come up with trees which are not similar to each other, so that once you do the final majority voting, you have variability, which basically prevents you from overfitting. Again, I'm not sure. I know that many of you might not be quite aware about deep learning, but one way to look at this idea and correlate to the concept of deep learning is the idea of dropout. So what do you do in dropout? You deactivate some nodes. So you force your decision to come from different paths, from different channels. Okay, hopefully once we go to the concept of deep learning, we'll discuss those ideas. But again, for you, some of you who have some background on deep learning, you can see some correlation here of the concepts, that this concept is somehow related also to the dropout concept in deep learning.
Doctor,
Yes.
regarding, for instance, other algorithms like posting and bagging, they seem to be more universal in terms that you can use any type of algorithm or machine learning approach. But in terms of random forests, you only use decision trees,
Yeah,
which is like, yeah. Why is it like more popular than like, because it's restricted only to decision trees?
okay, the idea is, from what I understand, it was an evolution. So what happened is, once the ensemble learning took place, its momentum, you had this idea of bagging and boosting. So the concept, the discussion was, okay, we can use data boost over individual classifiers which are decision trees. Why decision trees again? Again, because they are very having low bias. That's one benefit of decision trees, right? But we know the problem of decision trees are they have high variance. So the concept was, okay, why not use data boost with decision trees as individual classifiers? But then we said the idea is that, okay, yeah, AdaBoost is good, but it's quite slow and sequential training. So why not have something similar as a concept, okay, but then have it much faster? So the idea came of the decision trees, using individual decision trees in a forest, so as an ensemble. So it's basically an evolution of ensemble learning.
Okay.
I'm not sure if this was your question.
Yeah, thanks.
Yeah.
Hello, doctor.
Yes, please.
Can we say like the number of the trees, the more the number of the trees, the more the accuracy of the random forest?
Okay, that's an interesting point. Who can answer us? The more the number of trees, the more the accuracy of the random forest. Yes or no?
Since it is hyperparameter, I think we should experiment that.
Yeah, this is one answer, that we should experiment it because it's a hyperparameter. But what do you think
Also-
will be the trend?
Also, it's like increasing the complexity of a linear model or logistic. We can overfit if we increase the number of trees.
Okay, so one answer is that, okay, as you keep increasing T, you have this problem or possibility of getting overfit, right? So maybe no, not increasing the number of trees will give you better performance on the test. What do you think? Any other answer here? Anyone else who would like to contribute to this discussion?
I think that since you are randomly sample some from the training set, if you increase the number of the trees, you might have like some trees that have the same prediction, maybe.
Yeah, so one reason there will be a correlation between trees will be because if you have so many batches of bootstrap bagging like batches for training samples, there's more and more chances that one training sample batch resembles the other one. But then this is the nice point of random forest, that this is not the only point. Even the features are selected, drawn randomly. So still that will help you to decorrelate one tree from the another. But yeah, there is, the more you have, the more there is a possibility that the trees will be somehow correlated more. But then again, let's go back to the discussion we had before. In general, speaking of ensemble learning, what happens now? If you have more trees in your random forest, what do you think about the training error? you are expecting again it will keep decreasing down and down and down. Right? You agree? So if you have more trees in the random forest, our training error is naturally going to go down and down and down. But what happens to the test will be that you will go down, but then you, as a decision tree or individual complex classifier, you're not going to overfit that quickly. It's going to be robust overfitting. So you're going to get generally speaking a stable error rate, even if you keep increasing more and more trees. And if you really keep increasing too many trees, yani in the order of magnitude very high, then you might start getting some overfitting, but still quite low as compared to complex individual classifiers or decision trees, so to say. So still very, very robust to overfitting. So to go back to the answer now, if you're going to increase T, the hyperparameter T, if you keep increasing T, yes, you're going to get, in general speaking, lower and lower training error, but you're not going to get that much of a problem of overfitting. But at the same time, you don't guarantee that your test error is going to go down and down and down. It might go down initially, which is true, right? But then if you keep increasing more and more, you might see that it stabilizes. The error on the test set or the validation set stabilizes. It does not necessarily go down, but also it does not necessarily go up a lot. It stabilizes it. Is this making sense? So again, let's not forget that random forest is also an example of ensemble learning. So its behavior will also be somehow similar to other ensemble learning in that sense.
Doctor, since there is a lot of randomness, will we expect convergence to be much slower?
Okay, keep in mind what happens now is that in random forest you have individual decision trees. And these decision trees have very low bias. Naturally, it could have high variance, right? But then if you start aggregating those decision trees, what you find initially that variance starts dropping very fast. Is this clear? Because you have all those different decision trees having high variances, and then you're merging it by, let's say, majority voting, right? So your variance starts decreasing. But then, of course, once you had that sharp decrease in variance, your error mostly stabilizes it. So it's not that the error decreases very slow. Yeah, it does decrease very fast in the beginning, but generally speaking, then it starts stabilizing it very later on.
Doctor, excuse me, if you have like a very small data set, is it better to use the ordinary decision tree, or we should use the ensemble approach?
Okay, so another interesting question. If you have a smaller data set, is it good to use a single powerful classifier or an ensemble approach? Who can give us some insight into this?
If the number of feature is big, still random forest can can give a better performance because it will take a subset of the features and solve the
again,
problem.
just to clarify also, I don't know, let me say something, and the original question, we can see if this is the same question. If you say a small training set, again, smallness has two aspects, so to say. One basic definition I understand that was meant was that smallness means that we have very few training samples. Yeah, am I right?
Yes, that's right.
Yeah, that's right. So we have few training sample, but few also is a subjective issue if you consider the dimension of features. So few, if you have 100 training samples and 100 feature is different than if you have 100 training samples and 5 features. You see this time. So even the smallness is not only the number of samples you have, you can also look at it from the insight of how many features you have, right? And we know if you have more features and less samples, so the number of features compared to the number of samples is high, what's the common problem we can get into? If the number of features you have compared to the number of samples is high, that ratio is high, what's the problem normally you're going to expect? Underfitting, overfitting, what is it?
I think
Underfitting.
It's overfitting, right? If you have only let's say 100 features and you have if you have 100 features and 100 samples, you can always fit it perfectly. Right? So what happens is if you have high number of features as compared to samples, you're generally going to overfit. And in general, if you have low number of samples, there's a high tendency of overfitting it. If you remember our discussion in the first 2-3 weeks of the classes. If you have only few samples, very easy to overfit. So now keeping that into perspective, think about it. If you have a small data training set, small data set, is it a good approach to go for individual single classifier, or is it good to go for ensembles?
I think
What do
in
you-
general it's better to use ensemble because
Yes.
it's robust to overfitting.
Exactly. So in that sense, also it will be better to use ensembles because now it's more robust comparatively speaking to overfitting. I hope this idea is clear.
So the single trees, they are better, and that's the final conclusion.
We are saying that if you have a small data set, ensemble would be a better choice, a more safer choice than a single classifier.
Right.
Yeah. Okay. Is there any question before we move forward?
Just have a question.
Yes, please.
Until now, we have been talking about the same type of classifiers, for example, linear regression or logistic regression, and use them as ensemble. So does it make sense to use different types of classifiers, for example, decision tree plus logistic regression, for example,
Yes,
and
good.
ensemble them into, yeah.
Good question, actually. Yeah, and it's also done a lot in the literature. If you see, of course, you can use bagging, boosting in general speaking, but what you can also do anytime is to use a collection of different classifiers, okay? And then do some sort of combination, classify combination, majority voting, weighted majority voting, stuff like that. So that's also a good idea, right? And people do a lot of this. So what you can do is you can do, for example, my one classifier is knife base. Another classifier is SVM. A third classifier is, let's say, logistic regression. And a fourth one, we can have a decision tree or whatever, right? And what we do is then we somehow do the classifier combination. Classifier combination. How do we do this? Again, there are many literature discussions on that. One thing could be majority voting or weighted majority voting. You can find the mode, the number of classifiers which is giving the same class, the highest number of classifiers, right? In that sense, it could be different possibilities of doing it, right? So this is one idea here. So you can use different classifiers and try to combine them. Another approach could be what? Another approach could be you use same classifier. Let's say you use SVM. You use SVM one classifier, you use SVM a second one, or it could be anything. SVM is just an example, right? But what you do is you train this SVM on a subset of features, some subset of features, and this one on another subset of features. And it's good if the features are not correlated. This subset has features which are not highly correlated with this subset of features. And you have another subset of features. And then you do another classifier combination. This is another setup. And of course, using these two approaches, you can have another third approach where you have different features, the different classifiers, you combine all of that. That's also done, and it's also shown in the literature. So these are all possibilities. Yeah, you have to be careful in one thing. Once you have different classifiers, you have to understand that these classifiers should have different type of properties. Why? Because the problem is if all these classifiers have their error in the same region, you're not going to benefit a lot from combination. You see my point? And that's why it's a good idea to have different features for different classifiers. That's a much better approach. Why? If you have different subset of features you train on, your errors are done on different regions, generally speaking, if these features are not very highly correlated with each other. And then you do a combination that might be much more powerful, the benefits of it. So generally speaking, again, I'm repeating, if you do classify combination, right? And you're not very careful about that, what you will end up with, you'll get a performance which is similar to the best individual classifier you get. This is normally what you'll see. But if you do it in an intelligent way, how you select your classifiers, how you select your subset of features and you train and combine them, then you might see a bit of better performance, or generally speaking, a good performance as compared to individual classifier. There's another third way of classifier combination is, irrespective of you use different subset of features or classifiers, you have these individual ones, and then you have another classifier, right? And you do a validation set, you give these outputs. So what you do is the output of this classifier, the output of this classifier, and the output of this classifier is given as input to another classifier. And you train saying that if these are the outputs, this is the actual label. So based on that, you train another set, a second level of classifier, and gives you the final output. Is this idea getting clear? So here you're not doing a majority voting or some sort of weighted majority voting or some other combination. Here what you're doing is you're training another classifier to learn that if these classifier says me this as the output, what should be the final output? You learn that thing. This is another way of combining classifier. I'm not sure if this idea is getting clear. Is this clear?
Yes.
Yes.
So yeah, again, you can do ensemble learning in many different setups. And it's always a good area to try out. But generally speaking, the idea of bagging, boosting, random forest, they said that off the shelf, they are one of the most powerful classifier. So if you're not doing a lot of engineering, a lot of fine tuning, and you want some quick results, these ensembles, the bagging, boosting, and random forest, generally speaking, it works very nice.